Now, looking at the note sheet from yesterday, we got to this point here. Do we feel pretty comfortable with degrees, minutes, seconds? Yeah. It's not too bad, it's not too complicated. This way also, if you're looking at satellite positions and they give you these, we're really talking about degrees and location on the Earth, going north, south, east, west. Arc length. For a full circle, or for a circle of radius r and essential angle theta, an arc of length s given by s equals r theta is this here, where theta is the measure in radians. Note that if r is 1, then s is equal to theta, and the radian measure of theta equals the arc length. So if we have this here, a circle has a radius of 4, find the length of the arc intercepted by a central angle of 240 degrees, as shown. Well, s is equal to r theta, but for this here, theta has to be in terms, or in radians. We have to convert it to radians. So the first thing we're going to do is convert 240 degrees to radians by multiplying it by pi over 180. Now again, I'm going to use the 30xs, the yellow calculator. Goes 240. I don't know why I'm saying 540 because that's bigger than a circle. 240 times pi over 180 is the right one. So 4 pi over 3. So for our formula here, s is equal to, well, r in our case is 4. Our angle is 4 pi over 3. So the arc length, 4 times 4 pi over 3 is, yep. Questions on this here? Now, we're not going to get too much into this linear and angular speed, because I know we talked about this last year, but do you know the difference between linear and angular speed? So linear speed, well, if we talk about linear, we're talking about a line. Angular, we're talking about an angle, and that's the main difference. Consider a particle moving at a constant speed along a circular arc of radius r. If s is the length the arc is traveling in time, then the linear speed v of the particle is given by this here. Or we can talk about it in terms of a tire, because linear speed is going to be as it's moving around the circle in a linear motion. Angular is our rotation. And this also, I mean, they talk about this, we can see it in terms of an engine and tires, because again, the tires produce our linear speed, our momentum. Angular speed is normally talked about in RPMs, revolutions per minute. That's our angular speed. How fast is it turning compared to how fast is it moving forward? And that's really the difference between the two, because arc length divided by time. How much of the arc, how much along this circle is being laid down as the wheel progresses. And angular, how much from here to here, how fast is it rotating around the circle? That's the main difference between the two. Does that make sense? Central angle divided by time. How long does it take for the central angle to turn in a set given amount of time? Area of a circle. Area is equal to 1/2 radius squared theta. But that's really it. We're not going to focus too much on angular and linear projections. And 12, determine which quadrant each angle lies. So that's really just based off, I'll draw this up here. So if we had a Cartesian plane, in terms of degrees, 0, okay, there we go, 0, 90, 180, 270, 360. And then we could keep going around, keep adding 90. Where in the quadrants does this lie? Because our quadrants are 1, 2, 3, 4. So where does the angle lie in one of these 4 quadrants? Now, it's also going to do this in terms of radians, which is 0, pi over 2, pi, 3 pi over 2, and then 2 pi. And we can keep going around in this form. And if the angle is less than 0, we have a negative angle, negative radian. We can add 2 pi to it till we get a positive radian value between 0 and 2 pi, and then it's easier to pick out which quadrant. If it's bigger than 2 pi, we can subtract 2 pi from it till we get back into one of the 4. Or if you want to convert it to degree measures, you can do that too. Now, I'm going to go on and do one with y'all so that you can see this. So pi over 4, if we wanted to put this on the quadrant here, or coordinate plane, well, hopefully we notice that all of these radians do have pi in them, yes? So really the fraction we're looking at is 1/4. Here we have 0 and 2. Up top, pi over 2 is pi times 1/2, yes? And then on the far left, we have pi, which is 1. Down at the bottom, we have 1.5, then all the way back to 2. Well, where would 1/4 lie? Between, because we have between 0 and half, half and 1, 1 and 1.5, and 1.5 and 2. So that would be quadrant 1. Because 1/4 is between 0 and 1/2, so it's going to lie there in the first quadrant. Does that make sense? And that's all we're doing. So for question number 11, part A, quadrant 1 would be the correct answer. Is all it's asking. So 11 and 12, that's, you're just trying to label which quadrant they're going to lie in. 15 through 18, 15 and 16, determine 2 coterminal angles, one positive, one negative. So 15, 16, you need to give 2 coterminal angles, one's positive, one's negative. Need one of each. See here, 17, 18. Find the complement and supplement of each angle, if possible. So subtract it from pi over 2. For complement, supplement, we subtract it from pi. Not every one of these angles will have a complement, but every one of them should have a supplement. The only way they won't have a supplement is if it's bigger than pi, 1 pi, and it won't have a complement if it's bigger than pi over 2. So that's 17, 18. 25, 26. Determine the quadrant each angle lies. So this time they gave you degrees instead of radians, doing the same thing as 11 and 12. 29 through 32. 29 and 30. Determine 2 coterminal angles, one positive, one negative, given the angle. So this time it's in degrees. So the first ones were in radians, the second ones are in degrees. And then again, complement, supplement with degree measures. Those will be better or easier than radians. So that gets us to 32, 35 through 38, 35 and 36. Convert each degree measure from radians to degrees. or to convert each degree to radians. It says do not use a calculator. I don't mind if you use one. And then 37, 38, convert each radian measure to degrees. You can use a calculator for those there. Because that gets us through 38. 47 through 50, 47, 48. Convert each degree, minute, seconds to degrees in decimal form. 49 and 50, convert each degree to degree, minute, seconds. And that's it.